Hello, y'all. This is Darrell Barry Jr. Back continuing where we left off with some chains of coordinate systems. Ironically, the solution I was looking for, I found in my classical electrodynamics class. The way that they did the transformation of coordinates. So I think the wording in this text is just a little bit imprecise. Is how I see it. So we'll get started with that. The idea to review from the previous video is that we have a coordinate system, X and Y, and what we want to do is make a change to this coordinate system by rotating it. So for instance, if I was to rotate it so that the x-axis is now here, and naturally it might be better to just copy and rotate this whole thing. And that's directly on the cross point that is rotated. So the prime is the rotated axis. And what we have here is this angle, theta, which would be the same for both axes, is the amount that we've rotated the axis in. I copied the same thing over, so we know it's a accurate representation. It just looks a bit weird because for some reason our eyes can't properly see the angles. So that, I know to me it looks like the vertical one is a bit thinner, but it has to be the same angle. But I'll just reposition it so it's actually at the cross if I can. There we go. So the book that we work with and the one that you saw on the opening screen, it talks about the projection onto the uh, other axis. So in linear algebra, it talks about projection. Like if I was to project the x-axis onto the x prime axis, it'd be something like x prime dot x over the magnitude of x prime squared, and then x prime. But I think the wording is just, I mean, it is a physics book, so I guess it's not going to use uh, mathematical wording, but I am used to the terminology sort of matching it a bit better. So basically, the idea is it doesn't necessarily mean the projection. What we're doing is, so I'm going to take this axis here and I'm going to rotate it a bit so it's a bit more clear what I mean. So imagine that I flip that section. So the x is here, x prime is there, and we still have our theta in the middle. And what we want to do is find out what the coordinates will be if I find, let's say, a point in x. Like if this is P in x, and we know P prime will be rotated, so it'll be in this direction somewhere. So we want to find out what the for the P prime. So what I can do is for the x value, which means I want the x value, the x prime value, I'm going to basically make a triangle out of this. This would be my right angle. And since x prime is on the adjacent, this is going to be cosine of theta. So that means that x prime equals cosine of x. And that's the first part of it. And then I got to figure out the y one. So basically, you'll write it over again. It's going to be a wider angle. So this is my y prime. And you can see the y angle is a whole lot larger of an angle. But this theta will be different. So what do I call this theta 2? And theta 2 is 90 minus theta. So that's a trick. So I can, it's going to be the same theta. And that's how we put it in terms of theta. Another difference is um, I'm projecting that onto that angle. So when I rotate it, since I'm making this y prime horizontal, we still have cosine. So now this angle here is 90 minus theta. So I guess I could say this is x prime A and x prime B equals cosine of 90 minus theta x. And 90 minus an angle, or pi over 2 minus an angle, is sine of that angle. So then we have sine of theta. So this means that the x prime equals x cosine theta plus x sine theta. And scrolling back, what we did the other day, this is what we have. Oh, detail. I just noticed here, I forgot to mention that is actually the coordinate. So I think I put x for both of them by mistake. This one would be y. So basically whatever the y coordinate is for that one. So basically I'm taking whatever the x value is for our point. So in other words, our p, I can make it a bit more accurate. So our p is here. It's our p in our normal frame. And the y value is here. This is what I'm calling x, and this is what I'm calling y. So what I'm going to do is going to take the x value, multiply by cosine to get the first part, the y cosine 90 minus theta, which gives me sine, and that's how we get the x prime value. Then I end up doing the same thing for the y. So if I look at this, I have my x point here. Now, the thing is, it needs to project directly onto the plane. So hopefully I don't alter it too much. As we can see, in order to get the x value here, need to extend it, and it'll project onto the negative aspect of it back here. So if I also draw that, it'll look something like this. So this is still our x. but this is negative y. So when I make my triangle here, and keep in mind this angle here, this angle here is going to be 90 minus theta. So that means that that's this angle here. This angle is 90 minus theta. So now we have the y prime, the a part of it, equals the x value, whatever the x value is, cosine 90 minus theta. That's the negative y prime. So that's negative x sine theta for the first part. And the second part, which is going to be up there, is a bit easier. And we are projecting onto the positive. So this will be the y. This will be the y prime. So we have y. Still, again, we're using the y value to project the b part. This angle is theta for this one. As you can see, it's still marked there. So we have y prime b equals y cosine theta. So y prime equals negative x sine theta plus y cosine theta. And if we scroll up to what we did last time, we can see that that's what we have. So I think the wording is just odd. Hey, what's going on, Real Kindness? Glad to see you. So doing some oh yeah. So this is some absolutely non-dirt stuff. This is what I'm doing actually for my classical dynamics class and my classical electrodynamics class. Currently in both of these we have to rotate the axis. It's just my classical dynamics textbook is very oddly written. So it wasn't very helpful. I mean, it was helpful, but it wasn't as helpful on this topic as my classical electrodynamics textbook. So I'm going ahead and working it in that form. Any questions? Any comments about this transformation we did? If one comes up, I'll be on the lookout. So that was that, and that's how we get the transformation. So pretty simple. As long as you don't try to mix up different things. Welcome. Awesome. Um, so basically, all we're doing is if we have a particle or whatever it is uh, in the regular coordinate system, x, y, and what we're saying is, what if we want to rotate this coordinate system so that y is, let's say, there and x is here, so this would be x prime and y prime, and this will be theta. And we want to know if this is a particle at this point in the original coordinate system, what will the coordinate be in the prime coordinate system? So all I did was derive how we can calculate the new coordinate system. So basically, the if x, y is the position of the particle in the original coordinate system, then the position in the new coordinate system will be x prime, y prime, which will also equal x cosine theta plus y sine theta for the x value, and negative x sine theta plus y cosine theta for the y prime value. So what I did earlier is just showing that derivation and how we got that. But I think the book was using terminology that I'm familiar with from my linear algebra class. So when I was trying to do the linear algebra application for it, it just wasn't working, and that's why, because I think it's just worded badly. Something else I was thinking about doing before I went as well is the something that I'm having to do for both my uh, uh, classical dynamics and uh, quantum mechanics class. But I think you may have seen that I actually did it on MC2's channel, but technically I haven't did it on this channel. So let me actually show that, which is the derivation of gravity, which I had to do again for one of my homeworks. So I guess I should say the derivation of and did you see that? Because it might be. Did you see that on MC2's channel when I did the uh, uh, integrating gravity and acceleration to get the kinematic equations? Or if not, I can still do it. I mean, I could do it if you haven't, or if you want to see it again, I could do it as well. I could just make it another video. But I always think it's fun because I end up working it again. Like I worked a problem earlier today, um, where I guess technically I went through an example where we basically calculated how the average amount of distance a particle will travel if we took like a million random shots while it was falling off a cliff at random times. We had to use the gravity equation or the derivation for it. But this is pretty much all I wanted to show because the last video I did, I was trying to mix up the two. Yeah, it is nifty. I like it. Um, so what are we going to be doing in this class now? One of the things we did earlier in our homework, uh, we have to do things like calculate, for instance, I guess technically it's proofs, proving that if you have a particle that's falling at this pace from this location, prove that the time will end up being in this equation, or proving this, proving that. So it's pretty cool. And I could pull up the textbook really fast and show you some of the problems. And I'll probably close up, keep this one a short one. So I got the main thing worked out, which was the actually I could go on to the next part of the book. I don't remember where I left off on this book. So why don't we do that? Maybe I'll stay another 20 minutes and see where I was in my last reading. I'm a bit behind on my reading in this book, probably because I was focusing on some of my other classes. So, and by the way, the thing I did here, pretty easy to put it into a matrix notation. So if I was to say put this into matrix form, building off what was in this video, pretty easy to see how it becomes a transformation matrix. Um, which there's some detail to that. 'Cause right now I'm retaking my quantum class because if I would have just kept it the way it was, I would have got a C. But that professor is just, which is very hard. His exams are just crazy. I like the guy, but I think he has his classes a lot harder than it needs to be. Um, but this is one of the things I remember a bit from the class, which is if I, so this is basically the derivation that I got from earlier, that I derived earlier, the new coordinates in the other frame that we have right there. So what I can do is I can say x prime, y prime, make that into a matrix or a technically a 2 by 1 matrix or a vector. And I can have my cosine theta, sine theta, negative sine theta cosine theta. And what I did was just extract out the x and y as a vector, because if I did my matrix multiplication, the x would go down this column and the y would go down that column, so I go back what it was. And what it ends up outputting is this transformation matrix. So basically, I can use this matrix and take any set of vectors and simply apply this matrix to it to transform it into a different coordinate system. So, if I have x, let's say if my x was, I don't know, 5, 6, xy was 5, 6. I simply plug it into these values here, send it through that matrix, as long as I know the theta that let's say that the that the coordinate system was transformed by 45 degrees. I can simply plug this into this matrix here, and it will output the coordinate in the new transform coordinate system. So it ends up being pretty convenient. The reason why this brings up my quantum class is in quantum, which I'm sure I'll get to again in this class, um, if we're given uh, states of a particle, say we have a particle that's in a certain state and um, is represented by a matrix, and we want to see what the particle would be like in a different state. I do remember the professor applying this transformation matrix to the matrix rather than doing it the long calculation way, but we'll get to that. It's something that I'll get to when I stream in my quantum as we go along, but it is helpful to see where this matrix was derived from, how we could basically turn anything into another matrix form. Um, I was about to say that I'm not sure if it'll work if the angle went in this direction, but the fact is, if the angle went into this direction, we could simply make a bigger angle going in the other way. So it should work no matter what the angle is. If it's just if we're given a negative angle, I may have to convert it into a positive angle so it still works. By the way, how's my mic? Do you think my mic is better? I got a new mic since the last show I did. And so many people were saying I was muffled and everything. And so it's working better. Got a little boom to hold it up. So listen, glad it helps. So if anything else I can improve on it, let me know. I can make some tweaks to it. But so far it's been working. And so I like it. But awesome. That's pretty much all I had. Uh I'll probably let me know what topics are you interested in seeing? And basically, um, these are I'll bring up the screens of the classes I'm taking right now. Let me see here. There we go. So, of course, that's what I'm doing right now. But, and actually, let me size this a bit better. And you can let me know which subject you would like to see next. And what I'll do is I'll have a good presentation on that topic. So, right now, this is my classical electrodynamics class, which you've already seen. Uh, I'm also taking, okay, awesome. Sounds good. Quantum. So this is the quantum book we're using, Griffiths. So that's what I'll do. Um, I'll go ahead and the next video I do, it'll be on quantum. And we're just starting the semester as well. So you only know the very basics. I mean, even though I took the class before and I'm familiar with what's going to come, I still can't say I'm an expert at it because the fact is, since I was taking a class pass fail, I did enough to make sure I was going to pass. And the fact is, I was doing all I could, and I just knew I wasn't going to get an A. I knew halfway through I was only going to get a C. So at that point, I just did, what I needed to do to make sure I didn't fail. And now I'm taking it again. So I still can't say I understand it very well, but at least I know the basics. So this week, I'll make another video, Quantum Basics. And over the next few months, I'll be able to help you to get a good handle on quantum. So look for that. It'll probably be, oh, well, that's all right. I mean, this textbook here that you see right there, we go through the first 5 chapters, as I recall. And it only has like 7 chapters. Ironically, that reminds me. But since I got to UT and the previous schools I went through, they went through a lot less than the book. In UT, they pretty much always go through the whole book. Don't play. It's like if you taking a class, you're going through the book. Yeah, so it's 6 chapters, and we go through the first 5. Not all of 5, but we go through about 5, and I guess technically you would say 4.5. Like we don't get the full 5, but we do the fourth chapter plus like a little bit of 5. And yeah, they don't play. So you'll get a good handle on it. So awesome. Thanks for showing up. Always good seeing you, kindness. Next video will be quantum. I will say look for it. Let's say Friday, no later than Saturday, between Friday and Saturday, and I'll look for you then.